Hi everyone, my name is Aashay Kothari and I work in Dr. Prasad's lab. I was mentored by Badri on this work, who is a PhD student in Dr. Prasad's lab. My poster is on a wearable biosensor for monitoring inflammatory biomarkers from Eccrine sweat. Whenever a patient has any type of infection, their body naturally releases inflammatory molecules known as cytokines in the innate defense of their body. These molecules, also known as biomarkers, are used by physicians to help identify the progression of the inflammatory response during an infection. Two of the key markers of an inflammatory event are interleukin-6 and interleukin-10. Normally, the levels of these biomarkers are tested using a blood sample by trained personnel in a laboratory, which requires a significant amount of time to get the results. Moreover, blood-based sampling is a single-point measurement and is not suitable to continuously track the progression of infection for aiding in personalized medicine. In addition, blood sampling is invasive. And on the other hand, Eccrine sweat has shown great promise in detecting these biomarkers non-invasively and continuously, and it can be integrated into a wearable device. Therefore, we hypothesize that measuring cytokines from passive Eccrine sweat can help with real-time tracking of the progression of an infection. In order to achieve this, a wearable biosensor was developed that can detect both pro and anti-inflammatory cytokines, IL-6 and IL-10, from passive sweat. The developed sensor is highly sensitive and specific to the study biomarkers. This was achieved using highly specific capture probe antibodies on a semiconducting ionic liquid interface and being measured using electrochemical impedance spectroscopy. A metal semiconducting electrode was deposited on a porous polyamide substrate where sweat would be absorbed and it would wick through. Specific capture probe antibodies in choline dihydrogen phosphate ionic liquid solution was then functionalized on the electrode to capture the target analyte, IL-6 or IL-10 antigen, in the sweat. The binding interaction between the analyte and the antibody results in a charge modulation at the electrode solution interface, which is captured as an impedance response using non-Faradaic impedance spectroscopy by applying a very small input voltage. The use of choline DHP enhances the sensitivity of the sensor by increasing the electrochemical sensing response, which thereby increases the signal-to-noise ratio. Furthermore, ionic liquids enhance the stability of the capture probe antibodies by forming a layer around the antibody, preventing an interaction from water molecules. So, a calibration curve was developed by varying concentrations of target analyte in sweat. A blank baseline was measured before adding the dose concentrations. It is observed that the change in impedance response increases with increasing concentrations of the target analyte, confirming that we can rapidly detect the concentrations of IL-6 and IL-10 in sweat. A limit detection of 0.2 picogram per milliliter was achieved with a wide dynamic range of 0.2 to 200 picogram per milliliter for both target biomarkers, which is in the relevant physiological range. Additionally, the sensor demonstrated excellent specificity with no crosstalk to nonspecific biomarkers, validating the robustness of the sensor. Such a sensitive and specific response was achieved due to the use of highly specific capture probe antibodies in ionic liquid that amplify the sensing response by capturing subtle charge modulations due to binding interactions. Also, ionic liquids prevent charge screening by enhancing the electrical double layer within which the binding interactions occur. So in summary, a sweat-based biosensor of a wearable form factor was developed to directly detect inflammatory biomarkers from passive Eccrine sweat. The sensor demonstrated sensitivity for detecting an ultra-low concentration of 0.2 picogram per milliliter with a wide dynamic range of 0.2 to 200 picogram per milliliter. This was achieved by leveraging a novel sensing interface comprised of an antibody ionic liquid complex. Such a biosensing system that can sample low volumes of sweat to accurately and continuously report levels of biomarkers non-invasively enables real-time monitoring of health status. The developed sweat sensing device is envisioned as a wellness device to empower subjects for real-time monitoring of their health status and to allow physicians to provide patient-centric therapeutic intervention in the event of inflammation or an infection. The focus of our future work is to test in both healthy and sick cohorts to demonstrate the feasibility of the developed sensor platform for use on human subjects. Thank you all so much for spending the time to listen to my presentation.